Okay, so this time we're going to talk about invariance and assumptions associated with invariance. We are rapidly approaching the end of this module sequence. And yeah, so we got this and like one more after that. So let's push through. Okay, so let's start with invariance. So item response theory model parameters have an invariance property. What this means is that the examinee trait level estimates, so the theta estimates to an individual person, do not depend on which items are administered. And this in turn means that item parameters do not depend on a particular sample of examinees within a linear transformation. And why is this important? Well, it allows researchers to effectively link different scales that measure the same construct. And actually the wonderful Veronica Cole over in, well, she's at Wake Forest too, does a lot of cool work on this area with using various measures to like harmonize scales and get estimates that are equivalent across. It's super cool. So check her out. She's badass. But anyway, what they do is this linking allows examinees to be compared even if they've responded to different items. And this makes implementation of computer adaptive testing even easier. It allows for more random variation in items, as well as selecting items that have the best discrimination for whatever your estimated theta value is. There are major downsides, obviously, from the human standpoint. Computer adaptive testing is not so great. You can't go back, and there's others. But it, at least in theory, can be implemented well within the item response theory framework. Okay, so let's talk about assumptions, because, well, every model has them, even if we don't talk about them. So I'm going to talk about them. We got 4 that we're going to cover. We're going to cover monotonicity, unidimensionality, local independence, and qualitatively homogeneous population. Those are the 4. Okay, so monotonicity. So logistical IRT models assume a monotonically increasing function. So as the trait level increases, so does the probability of endorsing an item. So remember back to our item characteristic curves from last unit on item level information? Well, remember how I got all grumpy and sad when the curves like didn't perform as expected, like they didn't increase, or at least not have points of inflection? Essentially, this is the same thing. So if this assumption is violated, so say getting like a super high trait level actually decreases your likelihood of getting a question right, you're going to have a really hard time modeling it using a fancy logistic regression. And yeah, so if you have a nonlinear relationship between ability and performance, you're going to have a hard time. And so that's what monotonicity kind of requires. And you really can't apply item response theory, factor analysis, really any of these methods if the true underlying distribution is non-monotonic. I mean, it can flatline, but it can't curve inward or can't curve across itself. Okay, so unidimensionality. So we've talked about how this is an issue in classical test theory, but it's also an issue in item response theory. So in item response theory, like in all the models we've described in previous slides, individual differences are characterized by a single parameter theta. That's the Greek O. Now, multidimensional IRT models do exist, but they're not commonly applied because of many of the same challenges that are faced with factor analytic approaches with multiple constructs and whatnot. So, commonly applied IRT models, so all of the ones that you'll be exposed to in administering or receiving scores, GRE, SAT, etc., have a single factor, a single latent trait that accounts for all of the item covariance. These are often assessed using a specialized factor analytic model for dichotomous items, which, if we're being honest, is really just a slight reformatting of item response theory models. You can transform between the two in a fairly straightforward way, although that is beyond the scope of this class. Okay, so next we have local independence. So local independence assumes that item responses are uncorrelated after controlling for the latent trait. So when local independence is violated, this is called local dependence. And local independence and unidimensionality are related. So highly univocal scales can still have violations of local independence through item content. What do I mean by this? Say, for example, you have a test question that frankly gives you information about another test question. Say we were in a personality class, my personality class. I could have a question that said, given the 5-factor model, discuss conscientiousness within that context. So now that test question establishes that conscientiousness is somehow related to the 5-factor model. And then if I have another question, it's like, what are the 5 factors of the model? I can then go and use the knowledge I have from the test to improve my likelihood of at least getting 1 point out of 5, because the test says conscientiousness is part of the model. So you can get extra information, and the order effects of questions can have an impact too, which is an interesting area of political science, actually. But for this model to work, it assumes that item responses are uncorrelated, above and beyond whatever trait they are illustrating with their answers. So local dependence distorts item parameter estimates. It can cause item slopes to be larger than they should be. It also causes scales to look more precise than they really are. So it biases standard errors downward and makes them too small. In addition, when local dependence exists, it creates an artificially large correlation between 2 or more items. And this oversized correlation can dominate or override the latent trait, making it look like all your items hang together, when in fact they don't. It can create the illusion of a factor. So local dependence. So once we've identified local dependence, the next step is to address it. So one way to do this is to form testlets by combining locally dependent items. So make the entire chunk of information locally. And sorry, let me back up. So I actually do this for all of our quizzes. So every single quiz has multiple parts, because effectively each of those parts is correlated with everything else within that testlet. And so by aggregating within that testlet, so effectively our 3-item quiz is actually more like 26 or 27 items that are just clustered. So spoilers. So you can model in that local dependence by clustering it and kind of making subscales. You can also delete one or more of the locally dependent items from the scale so that local independence is achieved. So if you remove one of the items or modify it so it no longer gives your user extra information, you've addressed that problem. Now, obviously, this is an iterative process, and you will then, if you have to modify an item or remove an item, well, if you modify an item, you need to collect more data on it, because you can't just assume that it has the same level of difficulty and all that other information. Cool. So, qualitatively homogeneous population is a mouthful. I know this. The IRT model assumes that the same item response function applies to all members of the population. And this can be a big problem. And early in this class, I talked a lot about being mindful of disabilities and just individual differences above and beyond like whatever the individual trait is, because we can have differences in trait expression that are a function of culture and background and all these other things that aren't actually the result of trait level differences, but rather differences in trait expression. And that shows up here in qualitatively homogeneous population data. We assume for our IRT model that everybody performs the same, that they are all acting in similar ways. They may have different levels of ability, but their ability still performs the same for any given level. Now, differential item functioning is the fancy $20 word to describe this assumption violation. And it means that there is a violation of the invariance property. Diff is what this is shorthand for, occurs when an item has a different item response function for one or two or multiple groups. And therefore, examinees who are equal on the latent trait have different probabilities or expected values for endorsing that item. And the consequence of this is that no single item response function can be applied to the population if you have differential item functioning. Because if you do ignore this, what you've done is you've injected in bias into your model. You've artificially deflated scores for the group that does not perform in the classic approach. And I know I harp on this, harp is not the right word, but I talk a lot about this a lot, and I've thought about differential item functioning and disability and all that because obviously, I mean, not obvious, but because I have a lot of experience in this area from a personal standpoint, and I'm very, very aware that most people don't think about this as often as I do. But I encourage you to think about how whatever scoring or testing or assessment you're using, how it can penalize individuals who are different from you, who have different experiences and different ways of expressing whatever their latent ability is. So on that feel-goody note, I'm going to wrap up here. And next time we'll talk about applications. Bye-bye!